Here is a question, simple enough for a child to understand. Take any even number bigger than 2, 4, 6, 8, 100, a million, anything you like. Can you always build it by adding two prime numbers together? 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 100 is 47 plus 53. Go ahead and try any even number you want, and you will find it works every single time. People have now checked this for every even number up into the quintillions, and it has never once failed. And yet, after almost 300 years of trying, no human being has ever been able to prove that it is always true, not for lack of effort. Some of the greatest minds who ever lived have thrown themselves at this question, and it has beaten all of them. We do not know why it works. We do not even know for certain that it always will. This is the strange world we are visiting, the world of questions that mathematics cannot yet answer. And what makes them so unsettling is that they are not complicated, at least not on the surface. The hardest unsolved problems in mathematics are very often the ones you can explain to a 10-year-old in a single sentence, which is exactly what makes them so maddening. You understand the question completely, you can check that it seems to be true, and still the answer slips through every net anyone has ever built. By the end of this, you will also meet something far stranger than an unsolved problem, which is a question that has been proven to have no answer at all, not because we are not clever enough, but because the answer is, in a precise and permanent sense, beyond reach. Mathematics, it turns out, has discovered its own limits, and that discovery is one of the most profound things humanity has ever learned about anything. So, to understand why these problems are so hard, we first have to understand what mathematicians actually mean by solving one, because it is not what most people think. In everyday life, if you check that something works 1,000 times or 1,000,000 times, you call it true and move on. In mathematics, that counts for nothing. Checking 1,000,000 cases or 1,000,000,000,000 or a number so large you could never write it down proves absolutely nothing about whether the next case might break the pattern. What mathematics demands is a proof, an airtight chain of pure logic that shows a statement must be true for every possible case, all of them, forever, with no exceptions and no gaps. A proof is not strong evidence. It is certainty, the only certainty human beings have ever found anywhere, and it is permanent. A theorem proven by the ancient Greeks is just as true today as it was then, and it will be just as true 1,000,000,000 years from now. That is the prize, and that is why it is so hard to win. To solve one of these problems, you cannot just show that it looks true. You have to close off every possible escape route the universe of numbers might take, and numbers have an infinite number of escape routes. Almost all of the deepest unsolved problems gather around one strange family of numbers, the primes, so we should start there. A prime number is a whole number that cannot be divided evenly by anything except one and itself. 2, 3, 5, 7, 11, 13, and so on. Numbers like 6 are not prime because 6 is 2 times 3, but 7 cannot be broken down that way, so it is prime. The primes are, in a real sense, the atoms of arithmetic, because every other whole number is built by multiplying primes together and in exactly one way. They are the basic building blocks out of which all numbers are made. You would think that something so basic would be well understood, but the primes are one of the great mysteries of mathematics because they behave in a way that is half orderly and half completely wild. Here is what makes them so frustrating. The primes thin out as you go higher, becoming rarer and rarer among the larger numbers, and there is a rough sense of how quickly they thin out. But within that overall trend, where exactly the next prime will appear is maddeningly unpredictable. Sometimes two primes sit right next to each other with only one number between them, like 11 and 13. Sometimes you have to walk through a vast stretch of numbers with no primes at all. There is no simple formula that spits out the primes in order. They seem to be scattered almost at random, and yet not quite at random, because over the long run, they follow a definite pattern in how common they are. It is as if the primes are obeying some deep, hidden law that we can sense the shape of, but have never been able to write down. And the attempt to write down that law is the single most famous unsolved problem in all of mathematics. It is called the Riemann hypothesis, named after a mathematician named Bernhard Riemann, who proposed it in the year 1859, which means it has now resisted every assault for more than a century and a half. It is fiendishly hard to state in full, but the heart of it is this. Riemann found a way to connect the scattered, unpredictable primes to a smooth mathematical object, and he discovered that hidden inside that object was a kind of secret rhythm, a set of special points that seem to control exactly how the primes are distributed. The Riemann hypothesis is the claim that all of these special points line up perfectly along a single straight line. If they do, then the primes are as evenly behaved as they could possibly be, and an enormous amount of mathematics that we suspect is true would be put on solid ground. Mathematicians sometimes describe these special points as the music of the primes. The underlying notes that played together produce the seemingly random scatter we see. Riemann thought all the notes fell on one line. We still do not know if he was right. What makes the Riemann hypothesis so important is not just the primes themselves, but how much of mathematics has been built on top of the assumption that it is true. There are thousands of mathematical results that begin with the words, if the Riemann hypothesis is true, then, and go on to prove something useful. Whole towers of modern number theory are balanced on this one unproven foundation, waiting if someone proves it. All of those results snap instantly into certainty. If someone disproves it, finding even a single one of those special points off the line, a large part of that tower comes crashing down. We have checked by computer the first several trillion of those special points, and every single one of them sits exactly on the line, just as Riemann said. But remember, trillions of conformations prove nothing, because the line is infinitely long and there are infinitely many points still to check. The one that breaks the pattern, if it exists, might be waiting just past where our computers have reached. After more than 160 years, the Riemann hypothesis remains open, and most mathematicians consider it the most important unsolved problem in the entire field. Back to our opening question, which goes by the name of Goldbach's conjecture, after a mathematician named Christian Goldbach, who wrote it down in a letter in the year 1742. Every even number greater than 2, the conjecture says, can be written as the sum of two prime numbers. It is almost 300 years old. It has been verified by computer for every even number up to absurdly large values, and it has never failed. It feels obviously true, and nobody can prove it. Mathematicians have managed to prove things that are close, weaker versions that get most of the way there, but the full statement, the simple thing you could explain to a child, has never been cracked. There is something almost comical about it. We can land spacecraft on other planets and predict the behavior of particles to a dozen decimal places, but we cannot prove that every even number is the sum of two primes. Then there are the twin primes, and this one is lovely. Twin primes are pairs of primes that sit as close together as primes can possibly be, separated by just one number, like 3 and 5, or 11 and 13, or 17 and 19. As you climb higher into the numbers and the primes thin out, you might expect these cozy pairs to eventually stop appearing altogether. The twin prime conjecture says they never stop, that no matter how far out you go, there are always more twin primes waiting, infinitely many of them, all the way up forever. We find them even among gigantic numbers, but proving that they truly go on without end has never been done. There was a thrilling breakthrough in the year 2013 when a mathematician who had been working in near total obscurity proved that there are infinitely many pairs of primes separated by some bounded gap, a fixed distance. It was a stunning result, the first real crack in the problem, and a wave of follow-up work pushed the gap smaller and smaller. But the gap they can prove is still larger than the gap of just one that the twin prime conjecture is really about, and closing it the rest of the way remains beyond us. If you want the unsolved problem that most perfectly captures how something trivial to state can defeat the entire human race, it is the Collatz conjecture, and it is so simple you can play it right now in your head. Pick any whole number. If it is even, cut it in half. If it is odd, multiply it by 3 and add 1. Then take whatever you got and do it again and again. So if you start with 6, you get 3, then 10, then 5, then 16, then 8, then 4, then 2, then 1. The conjecture is simply this. No matter what number you start with, you always eventually crash down to 1. That is the whole thing. Try it with any number you like, and you will tumble down to 1 every time. People have checked this for every starting number up into the quintillions, and it has always worked. and it has never been proven. One of the greatest mathematicians of the 20th century looked at it and said that mathematics is simply not ready for such problems, that we do not yet have the tools to even approach it. A rule a child can follow, a pattern that holds for every number anyone has ever tried, and it sits there completely unproven, humiliating the smartest people alive. Not all of these mysteries are about numbers. One of the most important unsolved problems in the world is really about the limits of computers and what can be calculated at all, and it is called P versus NP. The idea behind it is something you have felt without ever naming it: the gap between solving a problem and merely checking an answer. Think of a jigsaw puzzle. Putting it together from scratch can take hours of hard work, but checking whether a finished puzzle is correct takes only a glance. Checking is easy, solving is hard. P versus NP asks a deep and precise version of this question. Are there problems whose answers are easy to check, but no matter how clever we are, genuinely hard to solve from scratch? Or is it the case that every problem whose answer can be quickly checked can also somehow be quickly solved, if only we were smart enough to find the trick? Almost everyone believes that solving is genuinely harder than checking, that some problems really are hard all the way down. But believing is not proving, and nobody has been able to prove it either way. And this is not just a curiosity for theorists, because the answer would shake the modern world. Almost all of the encryption that protects your bank account, your messages, and the entire internet relies on the assumption that certain problems are easy to check, but practically impossible to solve quickly. If someone proved that solving is always as easy as checking and found the method, that security could collapse overnight, and at the same time, we might suddenly be able to crack open problems in medicine, logistics, and science that are currently far out of reach. It is the rare unsolved problem that, depending on the answer, could either break the world or remake it. Most experts expect that solving really is harder, that the comfortable wall between the two will stand. But until someone proves it, that wall is just a guess. The Riemann hypothesis and P versus NP are both members of a very exclusive club, one that comes with a price tag attached. At the turn of the millennium, in the year 2000, a mathematics institute called the Clay Mathematics Institute announced a list of 7 great unsolved problems, the ones they judged to be among the most important and most stubborn in all of mathematics, and they attached a reward of $1 million to each. Solve any one of these 7 with a proof that survives the scrutiny of the world's experts, and you collect $1 million and a permanent place in the history of the field. They are called the Millennium Prize Problems, and they were chosen partly to echo a famous moment a century earlier, which we will come to, and partly to remind the world that mathematics still has enormous unconquered territory. Decades later, almost all of them remain unsolved. The $1 million uncollected, sitting there as a standing challenge to anyone who thinks they can crack what has beaten everyone else. Two of the seven we have already met, the Riemann hypothesis and P versus NP. The others are less famous, mostly because they are harder to even explain, but they are worth a quick look because they show how these mysteries reach into every corner of the mathematical world and even into physics. One of them, called the Navier-Stokes problem, is about something you experience every single day: the flow of fluids, the way water moves and air swirls. There are equations written down in the 1800s that are supposed to describe how a fluid flows, and engineers use them constantly to design everything from aircraft to weather forecasts. But here is the embarrassing secret. Nobody has ever been able to prove that these equations always behave sensibly. It is possible, as far as anyone can rigorously show, that under some conditions the equations could blow up and produce a nonsensical, infinite answer, a fluid moving infinitely fast at a single point. We use these equations all the time and they seem to work, but we cannot prove they will not somewhere break. Tied up in this is the deep mystery of turbulence, the chaotic churning of a fluid, which one famous physicist reportedly called the most important unsolved problem in classical physics. Another of the seven, the Yang-Mills problem, comes straight out of particle physics, and it asks for a proper mathematical foundation for the theory that describes the forces inside the atomic nucleus. Physicists use this theory every day, and it matches experiment beautifully, but the mathematics underneath it has never been made fully rigorous, and part of the challenge is to prove a feature called the mass gap, a particular property the theory seems to have, but which no one has proven from first principles. The last two, called the Hodge conjecture and the Birch and Swinnerton-Dyer conjecture, are so deep in abstract territory that they are genuinely hard to describe without years of training, dealing with the hidden shapes and structures that certain equations carve out. The point of mentioning all of them is not to fully explain each one, but to show the sheer range of what we do not know, from the everyday flow of water to the forces inside an atom to the most abstract structures the human mind has ever invented. 7 problems, $1 million each, and the field's best minds mostly stalled. But one of the 7 was solved, and the story of how is one of the strangest and most human episodes in modern mathematics. The Poincaré conjecture, named after the French mathematician Henri Poincaré, who posed it in the year 1904, is, very roughly, a question about the shape of space. It asks, in essence, how you can tell whether a shape is secretly just a sphere in disguise, no matter how it has been stretched or twisted, as long as it has not been torn or punctured. It sounds abstract, and it is, but it was one of the central problems in the branch of mathematics that studies shapes and spaces, and it resisted everyone for 100 years. Then, in the early 2000s, a reclusive Russian mathematician named Grigory Perelman posted a series of papers on the internet that it gradually became clear contained a complete proof He had done it. He had solved one of the 7 millennium problems, cracking a 100-year-old mystery, and then he walked away from all of it. Perelman was offered the Fields Medal, which is often described as the highest honor in mathematics, the closest thing the field has to a Nobel Prize, and he turned it down, becoming the first person ever to refuse it. When the Clay Institute awarded him the $1 million prize for solving the Poincaré conjecture, he refused that too, the entire $1 million, reportedly saying that he was not interested in money or fame. When the Clay Institute later tried to award him the $1 million, he turned that down too, calling it unfair because another mathematician, Richard Hamilton, whose ideas his proof had built upon, had contributed just as much. He withdrew from mathematics almost entirely and has lived out of the public eye ever since. It is a remarkable thing to sit with. A man solved one of the hardest problems in the world, was offered riches and the highest honors his field could give, and said no to all of it because the recognition did not match his own sense of what was fair. The Poincaré conjecture is, so far, the only one of the 7 millennium problems to be solved, and the person who solved it wanted nothing in return. The Poincaré story carries an important lesson, which is that unsolved does not mean unsolvable. And the single best illustration of that is a problem that tormented mathematics for more than 3 centuries before finally falling. It is called Fermat's last theorem, and its origin is the most famous taunt in the history of mathematics. Back in the year 1637, a French lawyer and brilliant amateur mathematician named Pierre de Fermat was reading an old mathematics book, and in the margin he scribbled a note. He claimed that a certain equation, a close cousin of the one behind the Pythagorean theorem you learned in school, has no whole number solutions at all once you go past squares to cubes and higher powers. And then he added the line that would drive mathematicians mad for the next 350 years. He wrote that he had discovered a truly marvelous proof of this, but that the margin was too small to contain it. Then he died without ever writing it down, leaving behind a claim with no proof and an infuriating hint that a beautiful answer existed somewhere, just out of reach. For over 3 centuries, the greatest mathematicians in the world tried to prove Fermat's marginal claim and failed. It became perhaps the most famous unsolved problem in mathematics, defeating generation after generation. Most experts came to suspect that Fermat had been mistaken, that whatever proof he thought he had was flawed, because the problem seemed to require mathematical tools that would not be invented until centuries after his death. Then, in the early 1990s, an English mathematician named Andrew Wiles, who had been obsessed with the problem since he was a 10-year-old boy who found it in a library book, did something almost unheard of in modern mathematics. He worked on it in complete secret, alone, for about 7 years, telling almost no one what he was doing, slowly assembling an enormous and intricate proof using deep modern mathematics that connected Fermat's old equation to entirely different and far more advanced areas of the field. In the year 1993, Wiles finally presented his proof to a stunned audience, and the world celebrated. The 350-year problem had fallen at last. But then came the cruel twist that anyone who has ever finished a giant project will feel in their stomach. As experts pored over the hundreds of pages of his proof, checking every step, they found a gap, a subtle flaw in one crucial part of the argument. The proof was not complete after all. Wiles had announced victory, and now, in front of everyone, his proof was unraveling. He spent the next year in a kind of agony, working desperately to fix the hole, at one point nearly giving up, until finally, with help from a former student named Richard Taylor, he found a way to repair the gap using a clever combination of approaches. The corrected proof was published in the year 1995, and it has stood ever since. Fermat's last theorem, after 358 years, was finally truly proven. It is the great reminder that these problems, however long they hold out, are not necessarily beyond us. Sometimes the answer is just waiting for someone stubborn enough and for the right tools to be invented. But notice, too, that the proof Wiles found runs to hundreds of pages of mathematics so advanced it did not exist in Fermat's time, which means that whatever Fermat thought he had scribbled in that margin almost certainly was not this, and the question of what, if anything, Fermat really had remains its own little unsolved mystery. The problems we have met so far are the famous ones, but the landscape of the unknown in mathematics is far wider than that, and some of the open questions are so simple they feel almost like jokes, except that nobody can answer them. Take perfect numbers, an idea the ancient Greeks loved. A perfect number is one that equals the sum of all the smaller numbers that divide into it. 6 is the first, because its divisors are 1, 2, and 3, and 1 plus 2 plus 3 is 6. The next is 28. The Greeks knew these, and they are lovely. Now here is the open question. Every perfect number anyone has ever found is even. Nobody has ever found an odd one, and nobody has been able to prove that an odd perfect number does or does not exist. This question is more than 2,000 years old, older than almost any other open problem in mathematics, and it is still completely unsettled. We have searched up to numbers with hundreds of digits and found none, but we cannot prove there is no odd perfect number lurking somewhere out beyond where we have looked 2,000 years, and we cannot answer a question about which whole numbers add up to themselves. There are open questions about numbers you use every day without a second thought, like pi, the number that shows up whenever you measure a circle. We know pi goes on forever without repeating, its digits marching off into infinity in no pattern anyone can predict. But there is a deeper property called being normal, which roughly means that every possible string of digits shows up in pi just as often as you would expect from pure randomness, that no digit and no pattern is favored over any other. Pi looks normal in every test we have ever run on its billions of computed digits, and we cannot prove it is. We do not know for certain whether somewhere far out in the digits of pi the randomness breaks down. There are even simpler sounding questions we cannot touch. Nobody knows whether pi plus the number e, another famous constant, is even irrational, whether it is a clean fraction or not. These are numbers at the very heart of mathematics, and basic facts about them remain genuinely open. Some unsolved problems are not about a single answer, but about a number so large it defeats the imagination. There is a branch of mathematics that asks, in any group of people or things, how large the group must be before some pattern is forced to appear, and the answers, called Ramsey numbers, grow so explosively that they become impossible to compute, even though we know they exist. The mathematician Paul Erdos, one of the most prolific who ever lived, captured this with a famous story. He said that if an all-powerful alien landed and demanded that we calculate a certain modest Ramsey number, or it would destroy the Earth, we should marshal every computer and mathematician on the planet and try, because we might just manage it. But if the alien demanded the next one up, he said, we should instead immediately attack the alien, because we would have no hope at all of computing it. The numbers are not infinite. They are specific whole numbers, and yet they are so vast that the entire computing power of humanity cannot reach them. The answer exists sitting there, and it is simply beyond us. Then there are the great modern dramas, where a claimed solution to a famous problem splits the mathematical community itself. The most striking recent example involves something called the ABC conjecture, a deceptively simple-looking statement about how addition and multiplication of whole numbers relate to each other, which would, if proven, unlock a huge amount of number theory in one stroke. In the year 2012, a brilliant and reclusive Japanese mathematician named Shinichi Mochizuki posted a proof of it, running to hundreds of pages of entirely new mathematics that he had invented almost single-handedly over decades, a theory so strange and so dense that almost no one else on earth could understand it. And that created an extraordinary situation, because mathematics decides what is true by having other experts check a proof, and here was a claimed proof of a major conjecture that the community could not agree was either right or wrong, because they could not fully follow it. Years of seminars and arguments followed, with some insisting the proof was complete and others pointing to a specific step they believed was an unbridgeable gap. To this day, there is no consensus. It is a strange and very human reminder that mathematics, for all its certainty, is still done by people, and that a proof is only finished when the community can actually verify it. It is worth balancing all this with the fact that problems do fall, sometimes after centuries, which keeps mathematicians hopeful. A conjecture about powers of numbers that had stood for over a century and a half was finally proven in the year 2002. And one of the most beautiful recent triumphs solved the problem about stacking spheres in higher dimensions. You know how a grocer stacks oranges in a pyramid to pack them as tightly as possible, proving that this everyday arrangement is truly the tightest possible packing in ordinary three-dimensional space was itself a problem that took centuries to settle. But mathematicians also ask the same question in higher dimensions, in four-dimensional space, eight-dimensional space, spaces we cannot picture at all, and these are genuinely useful because dense packings in high dimensions are connected to how we send error-free signals across noisy channels. In the year 2016, a mathematician named Marina Wiazowska solved the sphere packing problem in 8 dimensions, and then in 24 dimensions, with proofs so unexpectedly clean and elegant that other mathematicians described them as if she had found a magic key. These victories matter because they remind everyone that the wall of the unknown does move, that the unsolved is not the unsolvable, and that sometimes the answer to a centuries-old question is sitting in a dimension nobody thought to look in. It would give the wrong impression to make all of this sound like a pile of separate, disconnected riddles, because one of the deepest things modern mathematics has discovered is that these problems are secretly linked, often in ways nobody expected. The grandest example is something called the Langlands program, which is hard to describe but worth knowing about, because mathematicians sometimes call it a kind of grand unified theory of their whole subject. It began in the 1960s when a young mathematician named Robert Langlands wrote a letter sketching out a wild set of conjectures, suggesting that two areas of mathematics that look completely unrelated, the study of whole numbers and primes on one side, and the study of certain kinds of symmetry and waves on the other, are in fact deeply, intricately connected, mirror images of each other speaking different languages. If true, it would mean that a hard question about numbers could be translated into an easier question in the other world, solved there and translated back. Most of the Langlands program remains unproven, an enormous web of conjectures that has guided decades of research, and here is the lovely part. The proof of Fermat's last theorem, that 300-year mystery, was really the proof of one small corner of this vast web. Wiles cracked Fermat by proving a piece of the hidden connection between those two worlds. The biggest unsolved structure in mathematics is not a single problem at all, but a suspected secret unity running underneath the whole subject, most of which we can sense but cannot yet prove. There is also a human side to all this that is easy to miss when you only hear about the problems, and one figure captures it better than anyone, a Hungarian mathematician named Paul Erdős, who may have been the most prolific mathematician in history. Erdős had no home, no job in the ordinary sense, and almost no possessions. He spent his life as a wanderer, traveling from one mathematician's house to the next with a single suitcase, showing up on doorsteps and announcing that his brain was open, then working on problems for a few days before moving on. He published more papers with more collaborators than anyone who ever lived. He famously said that a mathematician is a machine for turning coffee into theorems, a line he borrowed from his colleague Alfred Rényi, and he kept himself working at an astonishing pace for decades. And he had a charming habit that captures the spirit of the unsolved problem perfectly. When he came across a problem he could not solve but found beautiful, he would offer a cash prize out of his own pocket to anyone who could crack it, ranging from a few dollars for a tricky question up to thousands for the truly hard ones. Some of those prizes are still unclaimed, the problems still open, the money still waiting. Mathematicians prize a check signed by Erdős so highly that even those who win one often frame it rather than cash it. The prizes are not just a charming quirk, because they point at something real about how this field moves forward, which is that a well-chosen problem with a reward attached can focus the attention of the whole world on a single question. Fermat's last theorem had its own prize long before the clay millennium money, a fund left by a wealthy enthusiast who, according to one story, had been so moved by the problem that it gave him a reason to keep living through a dark time, and who willed a large sum to whoever finally proved it. Andrew Wiles collected that prize after his proof was confirmed, nearly a century after it was offered. There is something genuinely beautiful about a problem so compelling that people leave money in their wills for whoever solves it generations later. Money that sits in trust across decades, waiting for a human mind to be clever enough to claim it. It says something about how much these abstract puzzles can matter to people, how a question about whole numbers can become, for some, a thing worth dedicating a life or a fortune to. And it is worth being clear that none of this is merely a game, because the unsolved problems of pure mathematics have a long and surprising habit of turning out to be enormously useful, often long after they were first posed, for no practical reason at all. The study of prime numbers was considered for centuries the most useless and abstract corner of mathematics, beautiful but good for nothing. Today, the difficulty of working backward from huge numbers to their prime building blocks is the foundation of nearly all the encryption that protects your bank account, your messages, and the entire internet. The abstract questions about how to pack spheres in strange high dimensions turned into the codes that let us send data across noisy connections without errors. Number theory, that was pure play 100 years ago, now runs the digital world. This keeps happening again and again, and it is one of the most reliable patterns in the whole history of science, that the deepest pure mathematics, pursued for nothing but the love of the question, tends to become, decades or centuries later, the hidden machinery of everyday life. So when mathematicians chase a problem that seems hopelessly abstract, with no use anyone can imagine, history suggests we should pay attention, because that very problem may turn out to run some future world. Before we reach the deepest limits of all, we need to take a detour into the strangest country in mathematics, the country of infinity, because it is there that some of the most mind-bending results live. For most of history, infinity was treated as a vague idea, a way of saying without end, something philosophers waved at but mathematicians did not really handle. That changed in the late 1800s because of one man, a German mathematician named Georg Cantor, who did something that sounds impossible. He found a way to measure infinity, to compare different infinities, and ask whether one is bigger than another. And what he found was so disturbing that much of the mathematical establishment of his time turned against him for it. Here is the question Cantor asked. We all agree there are infinitely many counting numbers, 1, 2, 3, and so on. And there are infinitely many fractions and infinitely many points on a line. They are all infinite, but are they the same infinity, or are some of these infinities bigger than others? It sounds like a meaningless question, because infinity is infinity, surely. Cantor found a brilliant way to make it precise. Two collections are the same size, he said, if you can perfectly pair them up 1 to 1 with nothing left over. The same way a shepherd who cannot count can still know there are exactly as many sheep as stones by matching one stone to each sheep. Using this simple idea of pairing, you can compare infinities without ever needing to count them, and the results were astonishing. Cantor showed that the counting numbers and the fractions, even though the fractions seem far more crowded, are actually the same size of infinity, because you can cleverly pair them up 1 to 1. So far, so strange, but tidy. But then he turned to the points on a line, all the decimals, every possible never-ending string of digits, and he proved something shocking, that this infinity is strictly bigger than the infinity of counting numbers. There is no way to pair them up. No matter how you try to make a list of all the decimals, he showed, using a beautiful argument, that you can always construct a new decimal that is missing from your list, which means the list can never be complete. The points on a line cannot be counted off one by one, even in principle. There are, provably, more of them. Infinity, it turned out, comes in different sizes, and there is an endless tower of larger and larger infinities climbing up beyond the first one, each one unreachable from the one below. This was one of the most original discoveries in the history of mathematics, and it earned Cantor not praise but hostility. One of the most powerful mathematicians of the day attacked him fiercely, calling him a corrupter of youth, and worked to block his career, while others would dismiss the new mathematics of infinity as a kind of disease, because the idea of completed, measurable infinities felt to many like a kind of blasphemy against the proper conduct of mathematics. Cantor, who struggled with severe depression, was wounded deeply by the rejection, and he spent time in and out of institutions in his later years, dying in poverty and ill health during the First World War. His greatest work, still fighting for acceptance. It is one of the sadder stories in the field. A man who saw further into the nature of infinity than anyone before him, and was punished for it in his own lifetime. The tide eventually turned completely. The same David Hilbert, who dreamed of a complete mathematics, declared that no one would ever expel mathematicians from the paradise that Cantor had created. Today, Cantor's work on infinity is woven into the foundations of the entire subject and the man who was called diseased is recognized as a genius who expanded the human imagination. And it is exactly here, in Cantor's Tower of Infinities, that the single sharpest question arises, the one that will lead us straight into the deepest result in all of mathematics. Cantor had shown that the infinity of the points on a line is bigger than the infinity of the counting numbers. So he asked the obvious next thing. Is there an infinity in between? Is there some collection bigger than the counting numbers, but smaller than the points on a line? Or do you jump straight from the one to the other with nothing in the gap? Cantor believed there was nothing in between, but he could never prove it, and the strain of failing to settle it haunted him. He had no way of knowing that the reason he could not prove it was the most extraordinary reason imaginable, that the answer, as we will see, is not hiding from us at all, but is something stranger than a hidden answer could ever be. All of this circles a question that turns out to be surprisingly slippery, which is what a proof even is. And in the last 50 years, that question has been forced wide open by an unexpected newcomer, the computer. The trouble began with a famous old puzzle called the four-color problem, which asks something a child could grasp. If you have any map, how many colors do you need so that no two regions sharing a border have the same color? People had long suspected the answer was four, that four colors are always enough for any map you could ever draw. But proving it for every possible map resisted everyone for over a century. Then, in the year 1976, two mathematicians finally proved it, and the way they did it sparked an argument that is still going on. They reduced the infinite variety of maps down to a large but finite number of cases, around 2,000 of them, and then had a computer grind through and check every single case, far more than any human could verify by hand in a lifetime. It worked. The theorem was proven, but it was the first time a major mathematical truth rested on a calculation that no human being could ever fully check, and that made a lot of mathematicians deeply uneasy. If you cannot read and understand every step of a proof yourself, is it really a proof? Or is it just a very strong promise from a machine? That unease only deepened with another famous problem, the question of how to stack spheres as tightly as possible in ordinary space, the orange stacking problem. The proof that the grocer's pyramid is the best possible arrangement, finally completed in the late 1990s, leaned so heavily on enormous computer calculations that the panel of expert referees, after years of effort, said they were only about 99% certain it was correct, that they could not fully verify every part. Imagine that, a mathematical proof that the experts could only call almost certainly right, when the entire point of mathematics is certainty. The mathematician behind it was so bothered by this that he spent more than a decade on a follow-up project, getting the whole proof rewritten in a form that a different kind of computer program, a proof-checking machine, could verify with total logical rigor every single step confirmed. That project succeeded, and it points toward what may be the future of the field, where the most complex proofs are written in a precise formal language and checked by software that cannot make a careless human error, so that certainty is restored, but in a new way, with a machine standing guard over the logic. And more recently still, a different kind of computing has begun to enter the picture, with advanced systems starting to help mathematicians search for proofs and even suggest new patterns worth proving, raising the strange prospect of a future where some of the work of discovery is shared with machines. But underneath all these practical questions about computers and proofs lies something far deeper, a discovery that there are limits to what any computer or any mechanical procedure at all could ever do, no matter how powerful. This came from one of the most important thinkers of the 20th century, an English mathematician named Alan Turing, who, in the year 1936, before real computers even existed, imagined them precisely enough to ask what they could and could not do. And he proved that there are questions no computer program can ever answer, not because the computer is too slow or too small, but as a matter of pure logic. His most famous example is called the halting problem. He proved that there can be no general method, no program that can look at any other program and correctly decide in every case whether that program will eventually finish running or whether it will get stuck running forever. Such a universal checker is not merely hard to build, it is logically impossible. There will always be programs whose fate no method can determine in advance. Turing's result and Gödel's, which we are about to reach, are deeply related, two faces of the same profound truth, that there are hard, permanent limits on what logic and computation can achieve. They tell us that even an all-powerful computer, given unlimited time, could not answer certain perfectly clear and precise questions, because those questions are not slow to answer, but provably unanswerable by any mechanical process. It is a humbling thing to learn at the dawn of the computer age that the machines we were just inventing came with a ceiling built into their very nature, a list of tasks they could never perform, knowable in advance. And it sets the stage perfectly for the deepest result of all, because what Turing proved about computers, a man named Kurt Gödel had already proved a few years earlier about mathematics itself. All of this raises a hopeful sounding question. If problems like Fermat's can hold out for centuries and then finally fall, is every mathematical question like that? Is every true statement provable if only we are patient and clever enough? For a long time, the greatest mathematicians believed the answer was yes, and the high point of that confidence came in the year 1900 in Paris, when one of the most influential mathematicians of the age, a German named David Hilbert, stood up and gave a famous address. He laid out a list of 23 unsolved problems that he believed should guide the future of mathematics, a kind of to-do list for the coming century. And several of those problems shaped decades of work, with a few still unsolved today. The Riemann hypothesis was on his list, but more than the list itself, what Hilbert captured was a spirit, a deep optimism that mathematics had no real limits. He believed that every well-posed mathematical question had an answer waiting to be found, that there was no such thing as a problem that was forever unknowable. Later, he summed up this faith in a ringing phrase, that in mathematics there is no such thing as we will never know, that we must know, and we will know. He had those words carved on his tombstone. Hilbert dreamed of putting all of mathematics on a perfect, unshakable foundation. The idea was to start from a small set of basic assumptions called axioms, the obvious starting truths everyone agrees on, and to show that from those axioms you could, in principle, prove every true statement in mathematics and never prove a false one, a complete and perfectly consistent system where everything true is provable and nothing false sneaks in. It was a beautiful vision, the ultimate triumph of human reason, mathematics finally made whole and certain to its very roots. And then, in the year 1931, a quiet, intense young logician named Kurt Gödel destroyed that dream forever, and he did it not with an experiment or a guess, but with a proof, an airtight piece of the very logic Hilbert worshipped. It is one of the most shocking results in the history of human thought. What Gödel proved is called the incompleteness theorem, and it says something that sounds almost impossible. In any mathematical system powerful enough to do ordinary arithmetic, there will always exist statements that are true, but that the system can never prove. Not statements we have not yet figured out how to prove, but statements that are genuinely, permanently unprovable from within that system, even though they are true. The completeness Hilbert wanted is not just hard to achieve, it is impossible forever for any system rich enough to be useful. There will always be true things it cannot reach. The roughly intuitive heart of Gödel's argument is dazzling. He found a way to make mathematics talk about itself, to encode within the language of arithmetic a statement that essentially says, this statement cannot be proven. Now think about what that does. If the system could prove that statement, then the statement would be false, which means the system would have proven something false, and the system that proves false things is worthless. So, if the system is any good, it cannot prove the statement, which means the statement is true, a true statement that cannot be proven exactly as it claims. Gödel had built out of pure logic a true sentence that no amount of mathematics could ever establish. He went further, and the second part is, if anything, even more humbling. Gödel also proved that no such system can prove its own consistency, cannot prove from the inside that it will never contradict itself. So, mathematics can never fully guarantee its own reliability using only its own tools. To be sure your system is sound, you would have to step outside it into a bigger system, and then that bigger system has the same problem, and so on forever, with no final, self-certifying foundation anywhere. The dream of a complete, self-justifying mathematics, the dream Hilbert carved into the spirit of his age, was not just unfinished. Gödel showed it could never be finished by anyone, ever. And he did it while Hilbert was still alive. There is something almost unbearably poignant about the timing, the great optimist declaring, "We must know, and we will know," and a young man proving, with the very logic the optimist loved, that there are things we provably never can. It is worth being careful here, because Gödel's result is one of the most misunderstood ideas in all of science, often stretched into vague claims that nothing can be known or that all truth is relative, which is not what it says at all. Gödel did not show that mathematics is broken or that we cannot trust it. The mathematics you use every day works perfectly. What he showed is far more precise and far more interesting, that the power of any logical system comes at an unavoidable price, that completeness and the ability to do arithmetic cannot both be fully had at once. It is a limit written into the nature of logic itself, not a flaw in our cleverness. No smarter mathematician, no faster computer, no future genius will ever get around it, because it is not a problem to be solved. It is a boundary proven to be permanent. If that all sounds too abstract, there is a concrete example, a specific real question that turned out to live in Gödel's shadow, and its story makes the whole thing tangible. It is exactly the question Cantor could never settle, the one we just met, of whether there is any size of infinity in between the counting numbers and the points on a line. The claim that there is nothing in between is called the continuum hypothesis, and for decades it was one of the great open questions, sitting at the very top of Hilbert's famous list. The resolution of the continuum hypothesis is one of the strangest things in this entire story, because it was not solved in the ordinary sense. It was proven to be unsolvable. In two stages, separated by about 20 years, mathematicians showed something astonishing. First Gödel himself, and then later a mathematician named Paul Cohen, who invented a powerful new technique to do it, proved together that the continuum hypothesis can neither be proven nor disproven from the standard accepted axioms of mathematics. You cannot show it is true. You cannot show it is false. Both possibilities are perfectly consistent with everything else in mathematics. The question of whether there is a size of infinity between those two has no answer within the rules we use, not because we have not found it, but because the rules simply do not decide it one way or the other. It is the clearest, most concrete illustration of Gödel's limit you could ask for. An honest, simple-sounding question about something as basic as the sizes of infinity that has been proven to be permanently undecidable. The answer is not hiding. There is no answer to find. It is worth coming back to the Riemann hypothesis one more time, because it sits at the center of a web of ideas so beautiful that it deserves a closer look, and because it connects astonishingly to physics in a way nobody saw coming. Start with the basic mystery of the primes, how they thin out. As you climb higher, the primes become rarer among large numbers, and there is a precise sense in which they do so, captured by one of the great results of the 19th century, the prime number theorem. This theorem gives a formula for roughly how many primes there are up to any given number, showing that they thin out in step with a particular smooth mathematical curve, so that even though you cannot predict exactly where the next prime will fall, you can predict very accurately how many primes there will be in any large stretch. The great mathematician Gauss noticed this pattern as a teenager, just by studying tables of primes, and it was finally proven around the year 1896 by two mathematicians working independently, using, crucially, the very tools that Riemann had developed. The prime number theorem tells you the average behavior of the primes, the smooth trend, but the Riemann hypothesis is about something deeper, about the precise size of the wobbles and deviations around that smooth trend. Riemann had discovered that the detailed distribution of the primes, all the irregular bumps and gaps, is controlled by those special points we mentioned, the places where his zeta function equals zero. And the Riemann hypothesis is the claim that all of these zeros line up perfectly along a single straight line. If they do, then the primes are as regular and well behaved as they could possibly be, with their deviations from the smooth trend kept as small as mathematically possible. This is why mathematicians often describe the special points as the music of the primes, because each zero contributes a kind of wave, a note, and adding all those notes together reproduces the exact, jagged distribution of the primes. The hypothesis says, in effect, that the music of the primes is in perfect tune. And here is where one of the most beautiful and unexpected connections in all of mathematics enters the story. In the 1970s, a mathematician studying the spacing between Riemann zeros happened to show his results to a physicist, and the physicist immediately recognized the pattern because it was exactly the same pattern that describes the energy levels of the nucleus of a heavy atom, the spacing of the quantum states of complicated physical systems. The way Riemann's zeros are spaced out along their line, it turned out, is statistically identical to the way the energy levels of certain quantum systems are spaced, a branch of physics called random matrix theory. This was a thunderbolt because there is no obvious reason on earth why the zeros of a function describing prime numbers should have anything whatsoever to do with the energy levels of atomic nuclei. Two areas of science that could not seem more unrelated, and yet there it was, the same deep pattern in both. This connection has led to one of the most tantalizing ideas about how the Riemann hypothesis might eventually be proven, an idea that goes back even earlier, sometimes called the Hilbert-Polya conjecture. The thought is this: if the Riemann zeros behave exactly like the energy levels of some quantum physical system, then perhaps there really is such a system, some quantum object whose energy levels are precisely the Riemann zeros. And if mathematicians or physicists could find or construct that system, its physics would automatically force the zeros to lie on the line, proving the Riemann hypothesis as a consequence. In other words, the proof of the deepest problem in number theory might come not from number theory at all, but from physics, from discovering a quantum system that has the primes built into its very structure. Nobody has found such a system, and it remains a dream, but the fact that the primes and quantum physics seem to be speaking the same language hints at some profound unity hiding beneath the surface of mathematics and the physical world, a hidden connection we do not yet understand. This is part of why the Riemann hypothesis is considered so important beyond just the primes themselves. It sits at a crossroads where number theory, analysis, and even physics all meet, and a proof would likely require or reveal deep new connections between areas of mathematics that currently seem separate. It is not just a hard problem to be checked off a list, but a kind of keystone, a place where the deep structure of mathematics seems to concentrate, so that understanding it would illuminate a vast surrounding landscape. Many of the greatest mathematicians of the past century and a half have been drawn to it precisely for this reason, sensing that it is not merely difficult, but central, that the answer, when it finally comes, will not be a small technical fact, but a profound new understanding of the hidden order running through the numbers, and perhaps through the universe itself. After more than a century and a half, that understanding still eludes us, which is exactly what makes it the most coveted unsolved problem in all of mathematics. It is encouraging, amid all these stubborn, open problems, to remember how often the wall of the unknown does move, and how, in recent years, problems that had resisted for decades or centuries have suddenly fallen, sometimes to clever individuals and sometimes to new ways of working together. Take the weaker cousin of Goldbach's conjecture, sometimes called the odd Goldbach conjecture, which says that every odd number above a certain small value can be written as the sum of three primes rather than two. This had been open for a very long time, and in the year 2013, a mathematician finally proved it completely, closing the case on at least the three prime version, even as the original two prime conjecture remains out of reach. It was a major achievement and a reminder that these problems are not necessarily eternal, that patient, brilliant work can crack what seemed uncrackable. Other long-standing puzzles have fallen in surprising ways. A problem about patterns in sequences of numbers, which the great Paul Erdos had posed and offered a prize for, and which had resisted for around 80 years, was solved in the year 2015 by one of the most celebrated living mathematicians in a traditional proof that finally settled it. And there has been progress on charmingly concrete puzzles too, like the famous problem of the largest sofa that can be maneuvered around a right-angled corner in a hallway. A question easy to picture and fiendishly hard to settle, on which a complete solution was recently claimed after the problem had stood open for nearly 60 years. Each of these victories chips away at the frontier of the unknown, and each one tends to introduce new ideas and tools that go on to solve other problems too. One genuinely new development in how mathematics gets done is the rise of massive online collaboration, which the internet has made possible for the first time. In the traditional picture, mathematics is done by lone geniuses or small groups working in quiet isolation, like Wiles in his attic or Perelman alone with his thoughts. But in recent years, mathematicians have begun launching open online collaborative projects where anyone interested can contribute ideas in public, sometimes hundreds of people chipping away at a hard problem together, building on each other's partial insights in real time. Several real results have come out of this open, crowdsourced way of working, including important progress on the gaps between prime numbers that built directly on that lone breakthrough by an obscure mathematician we mentioned earlier. It is a new model of mathematical discovery, less the solitary genius and more the global community, and it hints that the way we solve these great problems may itself be changing, becoming more collective, more open, and perhaps in time more powerful. And looming over all of this now is the question of what role artificial intelligence will play in the future of mathematics, because the same advances transforming so much of the world are beginning to reach into pure mathematics as well. There are already computer systems that can verify enormously long and complex proofs step by step with total logical rigor, catching errors that human reviewers might miss. And these proof-checking machines are increasingly used to give certainty to results too intricate for any person to fully hold in their head. More strikingly, the newest artificial intelligence systems have begun to assist in actually finding proofs and discovering new mathematical patterns, suggesting conjectures, and even sketching arguments, raising the genuine prospect that some of the great unsolved problems might one day be cracked with the help of, or even largely by, a machine. These unsettles some mathematicians and excites others, and it raises deep questions about what it would mean for a problem to be solved by an intelligence that cannot explain its reasoning the way a human can. Whether the Riemann hypothesis or the other great problems will eventually fall to a human mind, a global collaboration, an artificial intelligence, or some combination of all three, nobody knows, but the tools we bring to these problems are changing faster now than at any time in history. Underneath all these specific problems, solved and unsolved, lies a question even deeper than any of them, one that mathematicians and philosophers have argued about for thousands of years and still cannot settle, which is whether mathematics is invented or discovered. When a mathematician proves a new theorem, are they inventing it? The way a composer writes a symphony, creating something that did not exist before out of the human imagination? Or are they discovering it, the way an explorer finds a mountain that was always there, uncovering a truth that existed independently of any human mind, waiting to be found? It sounds like an abstract philosophical quibble, but it cuts to the very heart of what mathematics is, and thoughtful people come down firmly on both sides without being able to prove the other wrong. The case for discovery is powerful, and most working mathematicians feel it in their bones. When you prove something in mathematics, it does not feel like you are making it up. It feels like you are uncovering a fact that was true all along and would be true whether or not anyone ever found it. The fact that there are infinitely many primes was true before there were any humans, and would be true even if humanity vanished tomorrow, and would be discovered in the same form by any sufficiently advanced civilization anywhere in the universe. Mathematical truths have a stubborn, mind-independent quality, an inevitability that makes them feel less like inventions and more like features of some abstract reality that we explore but do not create. On this view, the unsolved problems we have discussed are not puzzles we have failed to invent answers to, but distant lands we have not yet reached, with the answers already there, waiting. But the case for invention has its defenders too, who point out that mathematics is, after all, a human creation built on definitions and rules that we chose, a language and a game whose pieces and moves we made up, even if the consequences of our choices then follow inevitably. The concepts of mathematics, the numbers, the shapes, the structures, are arguably idealizations and abstractions invented by human minds, and the fact that they then behave in consistent, surprising ways might just reflect the consistency of the rules we set down. The truth may lie somewhere in between, or the question may even be the wrong one to ask. But the very fact that we cannot resolve it after millennia tells you something profound about how strange and special mathematics is, sitting somewhere between the human and the eternal. This connects to perhaps the most mysterious thing of all about mathematics, something a famous physicist called the unreasonable effectiveness of mathematics in describing the physical world. Here is the puzzle. Mathematics is often developed as pure abstraction, with no thought of any application. Mathematicians chasing beautiful structures purely for their own sake. And yet, again and again, these abstract creations turn out, sometimes decades or centuries later, to be exactly the tools needed to describe how the physical universe actually works. The strange geometry of curved space, developed as pure mathematics, turned out to be precisely what Einstein needed for gravity. The abstract theory of certain mathematical structures turned out to be exactly the language of quantum mechanics. Over and over, the universe turns out to be written in mathematics that human beings had already invented or discovered for entirely unrelated reasons. Why should the cosmos obey the abstract patterns dreamed up in the minds of mathematicians? Nobody knows. It is, when you sit with it, one of the most astonishing and least explained facts about reality, that the universe is so deeply and precisely mathematical at all. And so the unsolved problems of mathematics turn out to be windows onto questions far larger than themselves. They are not just hard puzzles, but probes into the deepest nature of truth, of the human mind, and of the universe. Each one we solve teaches us something new, not only about numbers and shapes, but about what can be known and how. And each one that resists reminds us how much remains hidden even in the one domain where we thought certainty was possible. We found in mathematics the most reliable form of knowledge human beings have ever had. And then we found within it both questions we cannot yet answer and questions that can never be answered at all. And beneath it all, the staggering mystery of why this abstract creation of the human mind should fit the universe so perfectly. The deepest thing about the unsolved problems of mathematics may be that they show us with absolute rigor the exact shape and the exact limits of what we can know, and in doing so, they point beyond themselves toward mysteries we have only begun to glimpse. So step back and look at the whole strange landscape we have crossed. We started with questions so simple a child could understand them, like whether every even number is the sum of two primes, and found that some of them have defeated the entire human race for centuries, sitting there unproven, despite holding true for every case anyone has ever checked. We saw the deepest of them, the Riemann hypothesis, controlling the hidden rhythm of the primes and propping up towers of mathematics that wait, balanced, for an answer. We saw $1 million offered for each of 7 great problems and watched almost all of them stand untouched, while the one that fell was solved by a man who refused the money and the glory and walked away. We saw a 300-year taunt scribbled in a margin to finally answered, proof that patience and new tools can crack what seems eternal. And then we saw the deepest truth of all, that mathematics, the most certain form of knowledge human beings have ever built, contains within it true statements it can never prove, and questions that provably have no answer at all. And here is what I find worth sitting with after all of it. You might think that discovering the limits of mathematics would be discouraging, a kind of defeat, a sign that we should give up. It has been almost the opposite. Mathematicians did not stop when Gödel showed them the boundary. They kept going, and the field has been more creative and more alive in the decades since than ever before, precisely because knowing where the edges are tells you so much about the shape of the whole territory. There is something deeply human in this. We found the one kind of certainty that exists anywhere in human experience, the certainty of mathematical proof. And then we were honest enough and brave enough to map the exact places where even that certainty runs out. The unsolved problems are not failures. They are the open frontier, the proof that there is still an enormous amount we do not understand about something as simple as a whole number. And the questions that can never be answered are not a wall we slammed into. They are, in their own strange way, among the most profound discoveries we have ever made, because to prove that something is forever unknowable, you have to understand it more deeply than almost anything else. The smartest thing humanity ever did with mathematics may have been figuring out exactly what it can never do,